Okay. All right. So can you see my screen?
Yes, I can.
Okay. So this is just a basic introduction to machine learning class. Just to give you an overview of machine learning, a break away from all of the technical stuff that we've been doing since we started. Right. Machine learning is an exciting interdisciplinary field. So this explains that once you know machine learning, you can apply it anywhere: computer science, AI, information theory, philosophy, medicine, just anywhere, just with your basic knowledge of regression, classification, and clustering. You can apply your machine learning anywhere. Anyone can call you at any time. And you can use your knowledge of machine learning to help them solve their problems. Right? Machine learning is a subset of artificial intelligence. If you remember the relationship between machine learning, AI, and data science. So at the top of the bucket, we had AI, then we had ML, then we had data science, right? So machine learning is a subset of AI, which provides machine with the ability to learn from previous experience without being explicitly programmed, right? Quite correctly, the major part of machine learning is data. So of course, without data, there's nothing the machine is going to learn from. Data science now is a subfield. Machine learning is a subfield of data science that focuses on techniques for building models or algorithms that can learn by themselves by using data. So for example, in the last class, we talked about linear regression. Linear regression is a model or is an algorithm that learns from data that you can fit on a straight line graph, right? ML is quite different from statistics. Right? I'm sure you must have heard of statistical modeling. Machine learning is quite different from statistical modeling, although they do basically the same thing. They learn from data, but these are like the basic major differences between ML and statistics. So ML handles big data. That's why machine learning or data scientists are a thing. Why statisticians majorly handle small data. So a basic statistician can look at a small data set of, let's say, 500 or 1,000 and give you value from that data. But once your data set is entering 1 million, 10 million, then you need machine learning, right? In machine learning, there's minimal assumption because the machine does everything. But in statistical modeling, there's many assumptions because your model is small enough for you to generate insights from. In machine learning, data is usually split into training and test sets. Of course, remember I said that in the last class, while statistical modeling does not involve data partition. This one draws more on accuracy of performance, and this one draws more of relationship among variables. Now, the funny thing is that when we go into coding, before we do apply our machine learning models, we'll do some statistical modeling as well, just to learn from your data, to have some insights into what's happening within your data, right, before you go into machine learning. So machine learning uses metrics like sensitivity, blah, blah, blah. See all these metrics, we'll look at them very soon. Machine learning is about computer being able to think, learn with less human interventions. Like, it's just very simple. You want your computer to be able to learn from data and then make predictions based on what they've learned. So this is different between AI and machine learning, just so that when you go outside, you are not confused about what AI is or what machine learning is or what data science is. Like I've said earlier, machine learning is a subset of AI, right? So AI systems perform tasks as smart machines, e.g. apps, robots, right? A Tesla car, for example, is an AI system because it performs tasks on its own. While machine learning learns from data to predict an output. So there are two different things. AI is used to solve complex problems like humans do, while machine learning is used to make machines accurate for certain tasks. So like AI has a certain or higher level of abstraction. Abstraction is a word you will be learning when we get into Python. Abstraction just has to do with deeper amount of thinking, right? So AI has an higher level of abstraction than machine learning. AI focuses on the success of the system rather than the accuracy of the decision that the system makes. Why machine learning focuses on accuracy and reducing of errors, right? So later on, we'll be talking about how to focus on accuracy, how to reduce our errors. When you reduce your error, then you have a better model or a more accurate model, so to say. Examples: self-driven cars, robots, and whatnot. An example of machine learning models: we have face recognition, spam classification, Uber and and what have you. Component of machine learning, I said this in the last class, but one thing I didn't give you was reinforcement learning. So we have unsupervised learning, then we have supervised learning. Under supervised learning, we have classification and we have regression, if you remember. I'll send this slide to you just so that you can look at it more closely. Under unsupervised learning, we have clustering, where we have stuff like customer segmentation, recommender system, and dimensionality reduction. I will still talk about this one later in the class. One thing I've not mentioned is reinforcement learning. Reinforcement learning has to do with a situation where, let me see an example. So Tesla trains their cars, right? They train their cars to move from point A to point B. But because things change, right? Governments could decide to block one road and build another road from the top and build another road from where there wasn't a road, right? You need something like reinforcement learning because learning is continuous. So reinforcement learning systems are like human beings. They learn based on okay. There is a chess system that someone built. I think I'll send the article to you that learns every day. So that's reinforcement learning, where the system where real-time decisions need to be made, of course, like a Tesla car, robot navigation, skills acquisition, or game AI. So unlike unsupervised learning or supervised learning where you give your computer a data set and it has learned once and for all, reinforcement learning, you keep feeding the data set every day and it keeps learning every day. So difference between supervised and unsupervised learning, like I've shown you, supervised learning, you have output and your inputs. So your data set learns from the output and learns from the inputs. Our data are divided into training and test set. I've mentioned that before. It involves classification and regression. I've mentioned that before. Unsupervised learning is in a situation where
Are you there? I can't hear you anymore.
Okay, so supervised learning occurs where we have labeled output and input, right? And they're divided into training and test sets. While unsupervised learning, you don't have input. Sorry, you don't have output, you have only input, right? So they are called unlabeled data. It involves unlabeled data. So what you do is in unsupervised learning is that, for example, you have a customer data, right? You have customer data that looks like this. You have customer data that looks like this, right? Just customers, for example, excuse me, for example, customers in a pharmacy or customers of a fintech, right? You have customer data, millions of customer data, just inputs, no outputs. In clustering, what you do is that based on the characteristics of certain customers, you group them under certain groups, right? You group them based on their characteristics. There's no output, but there's just input. So based on certain characteristics, you just study them and then you just group data, right? So for example, if this retail company wants to reach out to customers that they think are going to buy, let's say an Xbox, because these are the guys who usually have bought Xboxes in the past. So you just group them into this box and then you reach out to them. So that's how clustering works, right? It works majorly in customer segmentation. Yeah, so as I've said, it involves unlabeled data. A clearer example of how to define classical machine learning. Once again, we have classification and regression, where we have pre-categorized data, right? Classification example is fraud detection or breast cancer detection, while regression example is market forecasting, where you want to predict real numbers. In unsupervised learning, we have three examples. We have clustering, right? Like I've explained. Then we have association mining, which I think I'm going to show you something on right now. And then we have dimensionality reduction, which I would explain later. Simple difference between supervised and unsupervised learning once again. The output is known here. Yeah, the output is known here. Yeah, this one is used to predict future outcomes accurately, while this one is just used for explaining relationships within your data, right? This one involves classification and regression once again. I said all of this. So steps involved in machine learning now. I'll need you to write this one down, although I'll send the slides to you. You collect the data set, of course. Then you pre-process your data set. You clean data. You look for missing values. You visualize your data to be sure that your data is intact. And then you perform feature selection, especially if you're talking about classified. Talking about supervised learning, right? Regression or classification, you have to perform feature selection. I think I've explained this in the last class as well. You perform data partition and build models. Data partition is where you have to divide your data into test and training sets. Then you build your model. For example, you could decide to use the linear regression model, right? Perform model selection. There are 100 models that you can use in machine learning, right? So you have to find out which model best works on your data. Then you validate your model and then you deploy your model for production, right? So these are the steps involved in the machine learning process. Feature selection is also known as variable selection. So sometimes you could have as much as 100 variables or 100 features. And most times those features are going to be very irrelevant. So you have to remove the features that are irrelevant, and that process is called feature selection, right? Improve data compatibility and to make training time faster. All models are useful. All models are wrong, but for some are useful. What this means is that in machine learning, the most accurate model is not necessarily what works in real life, right? So a model could have 99% accuracy on your computer, but when you test it in real life, it's failing. Your customers, it's not giving you real results in real life. So this is just to take your head away from accuracy. You could have the most accurate model, and then when you deploy it in real life, it gives you nonsense. So this is to say that the model that fits your customer in real life is the model that you want to look at. So this is an example of feature selection process, right? Removing irrelevant features. I mentioned that it's used to increase the model performance. Yeah, make training faster, easier to understand, easier to control. This is why feature selection is important. Feature selection versus feature extraction. Yeah, very important. Sometimes you'll be extracting some features from some features. So for example, let's say like I showed you somewhere here. Remember when I showed you the quadratic function? Can you remember how we multiplied the frontage of the house by the depth of the house? Sometimes you have the area, and the area is not what you need. The frontage of the house is basically what you need. So extracting frontage, right, from this area is what you call feature extraction. So this is to tell you that most times, if you have 24 hours, right, to perform a machine learning task, you use 20 hours to do feature selection and feature extraction, and then use the remaining 4 hours to train your model, right? Because feature extraction creates new features from the functions of the original feature set, whereas feature selection returns a subset of the original feature. So what we are saying is that, just simple English, feature selection, you find out which features correlate with your output variable, and you keep them. But feature extraction is creating new features from old features. And we are saying here that this is to avoid the cost of dimensionality, right? A feature could be so irrelevant, right? A feature could be so irrelevant that sometimes you don't need to delete it. A feature could be so irrelevant that sometimes deleting it affects the model, right? So what you need to do is look into the model and find out what feature you can extract from it, right? So for example, if I could say, I could have a feature that says maybe high blood pressure and multiply it by let's say blood glucose. This could be an entire feature, but this feature works badly with our model. And you can discover that if you delete this feature, your model performs worse than when the feature was there. So what you do is that look into the feature and find out what you can extract. So whether you extract blood pressure from the feature or blood glucose from the feature, or you extract high blood pressure. That's just like a very simple example. So to avoid cost of dimensionality, data partitioning, like I've said, we are going to partition our data into training sets for learning and then test sets for testing. We'll do this when we get to practical. And for cross validation is this guy the same. I need you to write. I'm going to send this slide to the group, and I need you to write down this classification methods, right? Because once you start to write your model, writing model is the very easy part. Like you can write 100 models a day, but what makes you a good data scientist or a good machine learning engineer is model evaluation. So you've written your model, you want to know how accurate your model is or how your model is going to work in real life. So predictive accuracy is the number of correct classifications, for example, for a classification problem over the total number of test cases. So I need to write all these things down. So we're going to look at them when we get to practicals. Precision and recall is another example, right? So for example, when we get to practical, we're going to be looking at a confusion matrix. This is what we call a confusion matrix, where you would have a positive, classified positive, and classified negative. So for example, let's say we are classifying malignant tumors, right? We'll have a confusion matrix like this, where you have, let's say you have 100 positive. So this is malignant, and this is benign, right? So let's say you have 100 there and you have 150 here. These two are the correct classifications, right? And this one here are the wrong classification. Let's say you have 15 wrong classifications for benign, and then you have 25 wrong classifications for malignancy, right? You need to look into this confusion matrix to find out what this model is telling you. Right? That's the reason for this confusion matrix, right? Out of this confusion matrix, we now break out our precision and our recall. Precision is TP over TP plus FP, while recall is TP over TP plus FN. We'll look at that later in practicals. We also have the F1 score. F1 score is 2PR over P plus R, right? It combines precision and recall into one measure. We have sensitivity and specificity. Forgive my accent, right? Write this one down as well. We'll be looking at why all these are important. We use a confusion matrix to introduce them. I've explained this earlier. We have an ROC curve. Right? An ROC curve is a better way to look at your confusion matrix, because it gives us your true positive rate. And there's a graph like this, right? So this is your random classifier, right? So ROC curve of anything from year to year is good. But when you have your ROC curve between year to year, then you have a very bad model. Right? So your ROC curve tells you how good your model performs or how terrible your model is, right? Which is basically the same thing as area under curve. So in when we get to R and Python, we'll be looking at real life data sets and we'll be applying all of these things on our data set. Just before we go, I wanted to show you the market basket analysis, which is a type of association. Which is under unsupervised learning, right? We use association rule mining to identify sequences. So what do you call it? Market basket analysis is used to predict future trends, solve problems in many applications, blah blah blah. It's just basic data mining. Data mining is just English, right? I think I have. Data mining is just English, right? So, for example, in a supermarket, you have customer one who comes to buy milk, bread, and cereal. Customer two comes to buy milk, bread, sugar, and egg. Then customer three comes to buy milk, bread, and butter. When we have 10,000 customers coming to buy groceries, right? We want to look at what items are associated inside one basket. That's why it is called market basket analysis. Now, this is usually used in supermarket or pharmacies, right? But you can use it anywhere. You can use it in fintech, you can use it in banking, you can use it in insurance, just anywhere. But we use supermarket data to explain it because it's very simple. What is market basket analysis? It's a technique based on buying a group of items. What merchandise are customers buying, and when are they buying the items? They are used to suggest new store layouts. So, for example, now that we know that sugar and egg are closely related, what you just do is that in your store, where you place sugar, try to make sure that you are placing egg beside it, right? Determine which products to put on special, type data to individual customers through loyalty cards or website registration. So techniques use classification, association rule mining, affinity analysis, visualization, blah, 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 blah. Again, it's used in point of sale transaction. So anywhere you have a point of sale transaction taking place, as a machine learning engineer or as a data scientist, you can actually help them derive insights from their data. And we are going to do this later in this course where we get to Python, right? So you can track customers over time, track what they are buying, tie customers to a particular product, tie products to product, tie orders to products, tie customers to order, and so on and so forth. I'll send you this slide as well so that you can read through. And I'm just basically doing this so that when we get into practicals, it doesn't look like I've not explained what we're about. So if a customer buys item A, we expect he or she will buy item B. That's just basically what we do in association. We associate one item to the next item, right? So that we can make decisions based on what's happening within our data. So market basket analysis might tell a retailer that customers often purchase shampoo and conditioner together. Target customers who buy flour with offers on their eggs to encourage them spend more on shopping basket. So basically what we are doing is that you're trying to increase your basket. So you are seeing egg in someone's basket and you're like, why not buy flour? Or you are seeing paracetamol, for example, in someone's basket and you're like, okay, why not buy, you are seeing malaria drug in someone's basket and you're like, oh, why not buy paracetamol? Why not buy vitamin C? Why not buy blood tonic? Why not buy blah, 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 blah? That's what we're basically doing in market basket analysis. So that's just an insight into basic machine learning concepts that I wanted us to discuss today. Do you have any questions? Do you have any questions? All right, please. All right, great. Thank you so much. Have a nice day.